Okay, so now let's switch gear and talk about sorting in general. So in computer science, searching and sorting are the two most fundamental and essential areas of concentration. How to do these two things most efficiently has been uh, one of the key um, problems that this field of computer science had ventured into from time to time. And doesn't matter which field of application one may be using the computer science concepts and algorithms in, this idea of searching and sorting is just present everywhere. Therefore, let's go deeper into understanding what are the different varieties of sorting algorithms and particularly what properties we might be interested in. So of course, one property that we keep bringing up is the time complexity. One may say space complexity also, but we had been mostly analyzing the time complexity. But we would introduce one more property for when we are evaluating certain sorting algorithms, and that would be whether a given sorting algorithm is an in-place algorithm. What does it mean by in-place algorithm? That means the sorting can be done in place within the same array that was presented before sorting. So no additional memory necessary. For storing the output of sorting. There's one more concern that that comes into play in the sorting that we are not going to spend too much time, and that is how stable is one's sorting. And by stability, what it means is that if I have the entries coming in, so if you see whenever we are using the term entry, that typically means the key and value sort of pair. And so if your entries are coming in key K1 value 1, then K2 value 2, K3 value 3. In this way, you have, let's say, n entries coming in. And you are interested in sorting with respect to the key, right? Now, it may happen that some of the keys are the same. So let's say you have K2 equal to K3. So after sorting, now one may say it does not matter because the value of the keys in both the cases are the same. So as long as I'm able to produce the overall sorted answer, I should be fine. So I can even have K3 comma V3, K2 comma V2. That should be fine because after all, these two values are the same. But the problem is that because there are other values that are stored in relation to the keys, therefore it violates the stability. So even though the values of the keys are the same, we would like to still preserve the original order in which my entries have been provided. So that is the essential stability aspect. But for now, let's just stick to these two criteria, the time complexity and the inplaceability of a given sorting algorithm. So sorting can be started. I mean, in one sense, we have already started discussing sorting because we had discussed the binary search tree based sorting, which is the in-place traversal of the binary search tree, which naturally also covers the split tree sorting, because split tree essentially is a binary search tree, and in an almost balanced condition. The first sorting algorithm you want to see is insertion sort. So the basic algorithm looks like this, that you start with an empty list, which is S. So the idea is that the S represents the sorted portion and I represents the input. So start with an empty list S and unsorted list I of n items. So basic insertion algorithm is that we take each item, let's say X in I, and we want to insert X into S in sorted order. And that's where the name insert comes from. So this is what is insertion algorithm, that we at every step we want to insert X into the right position. So if S is a linked list, then it would take order of n worst case time to find the right position. And therefore, so you can see for each item, if there are n items, so this overall for loop will be order of n. This overall for loop is order of n. And then this step of inserting X in the appropriate position, if it's a linked list, it will take order of n time to find the right position. And therefore, this is also going to be order of n. And if S is an array, then it's going to take order of n time to shift the higher items over. So in either case, whether it's a linked list or an array, it's going to take, this step is going to take order of n, and therefore the overall complexity for insertion sort, so the time complexity for insertion sort is order of n square. Now insertion sort is an in-place sort if S is an array. So essentially, therefore, you can take all the items and sort without any additional memory. So let's take an example. So suppose I have 6, 2, 7, 5. So we begin with I. So I is the unsorted list. And initially S part is empty. So at this point, S is empty. So from here, so we want to now 6, 2, 7, 5. So we now make this portion as the sorted portion, and this is the input. So we want to select. So we are going one step at a time. So you want to select the 6 and position it appropriately. So you can see that if you just shift this this boundary between the sorted and the unsorted, it does not make much of a difference because there is only one element at this point. So this was the first element. So we wanted to insert 6 in the sorted order. So because that's the first element, it can trivially just be the first position. Now the next one is we are trying to position 2 in relation to 6. So it will choose 2 here and then 6 here. So it is inserting the 2 in an appropriate place within the sorted order. And this remains 7 and 5. This is the input part. And then further, so from here, now the next item is 7. So you can see that it needs to find the right position within this. So it will find, so now the partition is here. So this is 5. So it found 2, 6, 7. So this is the sorted part, and this is the unsorted part. And finally, the last one to be inserted is 5, and it goes and keeps checking. So is 5 greater than 2? Yes, 5 greater than 2. So then next it checks, is 5 greater than 6? No. And therefore it inserts this in the right place. So it shifts and positions 5 here and 7 here. And there you get the whole thing as the sorted entry. So you can see at every step, we were, whatever is pointed to the arrow, so we were inserting into S. So here we inserted 6. Here we inserted 2. Here we inserted 7. Here we inserted 5. So this is the step what we executed, insert X into S in the sorted order. Okay, some important property of the insertion sort is that if your list is already almost sorted, then the insertion sort runs much faster. So this is overall in proportional to the number of inversions. So number of inversions, or we can say swaps, that might be easier to say. Okay. So this is an interesting point, that what is, so overall at every step you are inserting. So finding, so we saw that both in the case where the sorted list is maintained in either linked list format or the array format, it is going to have the quadratic complexity. And we also know that the quadratic complexity is useless. So finding the right compromise between linked list and arrays is the following. So if S is a balanced binary search tree, then you can imagine this whole insertion operation, inserting into S in the sorted order. We know that insertion operation in a balanced binary search tree is log of n. So then this will become n times log of n. So if S is a balanced binary search tree, then running time becomes order of n log n. All right, so that's about the insertion sort. Now let's talk about selection sort. So this is our second sorting algorithm for today. So selection sort. Selection sort is oftentimes also can be referred to as exchange sort. So this also has a quadratic complexity, order of n square. In fact, selection sort is actually worse than insertion sort, in the sense that in the case of insertion sort, when it's almost already sorted, it typically runs much faster. But in the case of selection sort, it always runs at the n square complexity. So what is the basic idea of selection sort? So you start with an empty list S. So S is initially empty, and unsorted list I of n items. And then for I equal to 0, I less than n plus I. So you're running it n times. So at every step, you're trying to find the smallest key. So let's say X be the item with, so item in I with the smallest key. So you remove X from I and append X to the end of S. So this process is essentially the selection step, where the name is coming from. So this is your selection step. So in this case, whether S is an array or a linked list, searching for minimum item. So because this involves looking for, this is where the search is involved. So searching for the item with the smallest key or minimum key in an unsorted list takes order of n time, and therefore this is order of n square, even in the best case in the sense when almost sorted input. So even in that case, this is going to take order of n square. So let's see with the same example. So we chose 6, 2, 7, 5. So the first, this is an unsorted input. So we have to select the minimum possible key at every step. So what is the minimum possible key here? So this is item in I with the smallest key. So the smallest key is 2. So you add 2 to the sorted portion of the array. And then you have here 6, 7, and 5. Okay, so this part is now our new input. Next, you're going to select from here what is the minimum key and simply append. So you select. So out of this, the minimum is 5. So it was 2 here. So you just simply append 5 after 2. And then you are left with 6 and 7. So here, this is the unsorted and this is the sorted. And then again from 6 and 7, you pick. So at every step, we are search for min here also. So search for min in I. Search for min in I. And again, search for min in I. And you append. So here between 6 and 7, 6 is the smallest. So it's 2, 5, 6, and then 7. So you can see it's already sorted, but it is going to still continue with its searching for the min operation. And I here, and then S, and the final step, there is only 7. So this is the final sorted order after going through the selection and appending at every step. So very interesting insight here. So at every step, look that we are looking for the min at every step. And we just learned how to efficiently look for min. So if you have a data structure like binary heap, then search for min is simply order of 1 or constant time complexity. So if you replace I with a heap, then this selection sort algorithm turns into a heap sort algorithm. So now we can look into, so here also we demonstrated how this can be an in-place algorithm, because we were So in this case also it's an in-place algorithm because we were not paying any additional storage. All right, so now at this point, we are ready for showing the heap sort algorithm. So this is our third category of sorting algorithm. So heap sort is essentially a selection sort where I is a binary heap. So what are the steps here? So you start with an empty list S and unsorted list I of n items. And then throw all items in I. So all items in I throw into a heap H. Now at this point, ignoring the heap order property. So you know what that means. You're just storing it in that array representing the heap starting from index number 1. And then on that, so on that H, we call bottom up heap, and we discussed how to do that. One important point is that this bottom up heap, unlike when we were adding onto the heap one by one and maintaining heap property, we showed how it takes n log n. But the bottom up heap, in the way we described, today we'll not go into the proof for that. It actually takes linear time. So which is where you are just throwing into the heap and then you are looking for the last internal node, and then you are walking backward and then doing the bubble down operation. That whole series of steps takes linear time. And then after that, then you, just like the standard selection sort, so you go I equal to 0, I less than n plus plus I, and you do x equal to h dot remove min. So now, because this is now a heap, so remove min, if you recall, that takes log n time, because when you're removing the min, essentially you're removing from the root, and then you're placing the last entry after removing the root in, you're placing the last entry into the position number 1, and then it violates the heap order property, and then we do the bubble down operation again, and that is because of which it's a log n time complexity. And then after you extract, then you do append x to the end of s. And so because this step is now log n time, this removal of min, and this for loop is running order of n times. So overall complexity for doing the heap sort is therefore order of n log n, because this outer for loop n, and then you have the log n. So this is the complexity of the heap sort. So heap sort is also an in-place sort. So how do we maintain the heap in place? Is that, so you maintain a heap backward at the end of the array. So if you take 6, 2, 7, 5 as our initial input, so here you've got 5 here, and then 7, 2, and 6. So if we just randomly, suppose this is some random order in which we are throwing the heap, then after applying the bottom up heap, we will get essentially 2, 5, 6, and then 7. Oh. So now if from here, let's say because of applying the heap order property, so you can see 5, 7. So we are, one important point to note here is that we are maintaining the heap backward. So it's 5, 7, 2, 6, 5, 7, 2, 6. And here this becomes 5, sorry, it's 2, 6, 5, 7. So this is the heap that we get after we are done with the maintenance of the heap order property. So after that, we do remove min here. Now we are approaching the selection sort mechanism. So when you remove min, then net 2 gets removed. So you insert 2 here, sorted area. And then you have, after the remove min, you have 5, 6, and 7. So maintaining the heap order property. So you will have 5, so the heap order in the reverse direction. So we again maintaining the heap backward. So 5, 6, and 7. This is your unsorted list. And then on this we do remove min. And this leads to extracting 5 and appending 5 here. And then you have the remaining entries, which is going to maintain the heap order property after removal of 5. So 6 and 7. So again, reverse order. So 6 and 7. So this is your unsorted. This is the sorted. And you do remove min one more time. So that gives us 2, 5. So 6 is extracted. So 6 comes next and 7. So this is your sorted. This is your unsorted. And you can see that this is already at this point, we are done. Okay. So some important notes for heap sort. So heap sort. So here we had demonstrated how heap sort is an in-place sort, and it is excellent for sorting arrays, but clumsy when it comes to linked list. So when it comes to sorting arrays, heap sort, you can see, is a natural algorithm of choice compared to when the inputs are coming in the linked list form. So that's all I wanted to cover in terms of the fundamental in-place sorting algorithms for today. But also I want to surprise you with another additional sorting algorithm in a separate recording. So let's stop this recording for now.